Hi, and welcome to the problem session of Lecture 14, which covers more advanced topics in multivariate calculus. So we're going to do things like compute here the gradient, the Hessian, the Jacobian, and so on. And also we'll get some more practice doing partial derivatives. First, though, we're going to talk about the difference between total derivatives and partial derivatives. I'm going to start by defining a function of x, y, and t equal to 3xy minus y squared plus the t. Now here t is a parameter. It doesn't have to be. This will work for any other variable z, for instance. And in the problem set and the exercises in the book, we use z instead of t for this thing. But it doesn't matter at all. They're the same thing. The important point is that x and y are going to be functions of t themselves. So now we can use this to understand the difference between the partial derivative and the total derivative. So first we're going to look at the partial derivative. The partial derivative ignores all other variables, as it always does, and treats them all as constant. So the only thing it takes the derivative of is the e to the t over here. So the partial derivative returns e to the t. The total derivative, however, is computed as so. It's the direct effect of t on f plus the indirect effects mediated by x and by y. Okay. So we can do this. We can plug in all the different values here. We have this one is still e to the t, and then this one over here, partial f partial x, is just 3y. That's the only place x exists in that function, is right there. And then dx dt is 6t. And then finally, the last term here, y appears in two places, the first term and the second term. And dy dt is 2t. So there you go. There's a total derivative. If you wanted to, you could get rid of the y and the x completely, leaving only t if you so desired. You could just plug in for the y's. You'd have 18 t squared times t is t cubed plus, let's see, 6t cubed times 2t is 12t to the fourth minus, and then the y would be 2t squared 4t cubed, which would equal 12t to the fourth plus 14t cubed. Either way, it's right, it's correct. It doesn't really matter how you do it. There you go. No difference between the total derivative and the partial derivative. The total derivative gives you the entire change in f with respect to t, both the direct change, that's a result of direct changes in t, and also the indirect changes in f that result in the fact that t changes x, and then x changes f, or t changes y, and then y changes f. So it gives you the direct and the indirect changes in f. Both mechanisms, and in general, when we're doing things like computing comparative statics in the next and last lecture, we're going to care about the total effect of a parameter and not just the partial effect of a parameter. Okay. So there's a total derivative and partial derivative. That's an example of that. Let's now do some gradients and Hessians. Now in the problem sets, we have some three variable cases. In the screen, we're going to do two variable cases to make life slightly easier for us. So that's, we use the function 2x squared plus 5xy plus y squared. First, we're going to calculate the gradient of the function. Well, the gradient of the function is a vector, and each element of the vector is the partial derivative with respect to the variable. So here's partial f partial x, and here is partial f partial y. We're going to see what that is. So the first one, x appears in two places. The first term, this derivative is 4x. The second term is derivative is 5y. And then y appears in two places. The first one is 5x. And the second is 2y. And that's our whole gradient right there. Okay. Now we want the Hessian. The Hessian is the matrix of second order partial derivatives. So on the diagonal is the straight second order ones, and the off diagonal is the cross partials, mixed partials. Okay, well, the second order partial squared f partial x squared takes the first element of the gradient and takes the derivative with respect to x. That's just 4. the cross partial takes, in this case, the first element of the gradient with respect to y. That gives you 5. Then here the cross partial is the same. You can check it by taking the second element of the gradient with respect to x. That's still 5, as it has to be, because the mixed partials are always the same, regardless of the order you take them in. And finally, the second partial with respect to y, second order partial with respect to y is just the second element of the gradient partial with respect to y, which is 2. And there you go. There's the Hessian. And again, larger ones are more complicated, but no more theoretically complicated, just more algebraically and calculus-wise complicated. There's more stuff to do, but not actually more theoretically complicated. Now we can ask the question, is this Hessian tell us that this function is concave, convex, or neither? Well, a convex function is one that curves upward, and if you have more than one dimension, right, it looks like a bowl, for instance. So we know a convex function has all positive eigenvalues, whereas a concave function curves downward, like an inverted bowl or a cap, I guess, and has negative eigenvalues. If it is neither all positive nor negative eigenvalues, then it's an indeterminate. The Hessian is indeterminate, and you have a potentially saddle point where you might have it curving one way, upward in one direction and downward in a different direction. So we can compute the eigenvalues for this Hessian. We get 4 minus lambda, 2 minus lambda, 5, 5. This determinant is going to be 4 minus lambda times 2 minus lambda minus 25 equals lambda squared minus 8 lambda minus 17. And that's some algebra. And again, you can pause here if that was too fast and make sure that it's all clear. The roots for this thing, which you can get by doing, say, the quadratic formula, 3 plus or minus the square root of 26. The square root of 26 is slightly more than 5, so one of these is positive and one of these is negative. Therefore, it is neither convex nor concave. We have an indeterminate case. Okay, so that's an example of this. And again, we have little longer examples in the problem set. There's a longer example in the problem set, and also some more examples that are also longer in the exercises in the book. Okay, so that's that. And one more example I want to do is Jacobian. Let's start off with a vector-valued function over here. Here we will do 3 variables. And the vector, I should write a vector here. And the vector-valued function has first element x squared minus cubed z. The next one, the natural log of x times e to the y. And the last one, z cubed e to the x. We want a Jacobian. How do we do a Jacobian? How do we figure out what it is? Well, we go through in the Jacobian, each element jik is equal to the derivative of the function, the ith component of the function, with respect, dot there, with respect to the kth variable. So, Jacobian, first we do, the first row is all the first element of the function. So there's an x here, is 2x. There's a y over here, 3y squared z, because z is a constant with respect to the partial derivative. And the y cubed is a constant with respect to the z. Excuse me, I forgot the z there. I'm sorry, I forgot the negative sign is what I mean to say. There we go. And let's see, the next one is the second element of the function. That's the next row of the Jacobian. So there's an x. The derivative of natural log is 1 over x. So there you go. E to the y is a constant with respect to that partial derivative. This stays the same because the derivative of e to the y stays e to the y. And finally, there's no z there at all, so that's a big 0. Okay. Finally, the last row is corresponding to the last element of f. The e to the x stays the same. Z is a constant with respect to x. There's no y there at all, so it's a big 0. And finally, the e to the x stays the same. We pull down a 3 and get z squared, because the derivative of z cubed is z squared, 3z squared. And that is it. And there's a Jacobian. That's it. So again, there's nothing really new in all this stuff other than understanding how to relate the Hessian to concavity or convexity. Everything else here is just applications of applying partial derivatives and putting them in the appropriate spots in matrices or vectors. That's really it. That ends this lecture problem session. Thank you very much.